Hello, my name is Gasco. Today I'm going to present the work done for the organization of the SocialDisNER Shared Task and its results, which is part of the Social Media Mining for Health workshop, the most relevant workshop on health information extraction in social media. SocialDisNER is a shared task that focuses on the recognition of disease mention in Twitter text. I would like to present why it's impactful and important to produce corpora with social media data. Without any doubt, social media has become one of the main tools for sharing information with people who are part of the same online community. Social media platforms are used by more than 4.2 billion people. These users spend an average of 2.5 hours to communicate with their network by means of multimedia content, such as video and images, but also text messages, which is the type of data we are going to work with. In recent years, the social media content has been extracted from these platforms and used for research purposes on various topics, such as detection of problems in urban environments, like noisy events in populated areas. It is very significant that a big amount of research has been carried out to extract health information from online social networks. For example, projects have been developed to extract knowledge about the psychological state of different population groups. Many of the work has also been focused on extracting insights about abuse of drugs and the study of their side effects. And especially after the pandemics, we have experienced in the last few years that social media are being used to extract knowledge about new emerging pathogens that are dangerous to public health. The advanced level of biomedical information extraction technologies from social networks, especially in English, is thanks to initiatives such as the Social Media Mining for Health workshop, which for years has been organizing a shared task with different tasks to generate language resources that allow research to be done through text analysis published in social networks. But why organize this shared task with text in Spanish? Well, Spanish is the second language with the most native speakers in the world, which makes it a very relevant language on the internet. In fact, it is the third most used language on the internet at the moment. Regarding social networks, as an example, these graphs shows the ranking of use of different languages on Twitter, the most important microblogging or online social network. Spanish has always been one of the most popular languages over the time, but this has not translated into the creation of resources to train artificial intelligence systems to extract and analyze information from this platform. This is especially remarkable in the intersection area between social media and health. The few existing resources focus on text classification datasets, such as DOS and Copos Corpus, focused on classifying opinion text about medicines according to their sentiment, and also we have the SAT Corpus, focused on detecting tweets dealing with anorexia content. In the area of information extraction, resources are even more limited. The most relevant corpora are the Spanish ADR, created to detect drugs and adverse effects in tweets, and the ProfNER corpus for the detection of biomedical professions, presented at last year's Social Media Mining for Health workshop. The lack of resources is an opportunity to generate a corpus of impact and high interest to the biomedical community and the natural language processing field. But why this is detection in the shared task? Why do we focus on disease mentions at SocialDisNER? Well, to generate a high-impact dataset, we need to focus on entities that allow other researchers to detect relevant health content in social media. And disease mentions are important to detect this type of content. On the one hand, disease mentions can be used to detect documents that deal with health content, but also other types of tweets that contain relevant information about procedures or symptoms, which could facilitate to extract relevant health data for research studies and training new NLP systems. For example, in the second and third tweets in the slide, we can see how mentions of a mentioned disease co-appear with other types of entities, such as medical procedures, in this case vaccination, and symptomatology, sweating and difficulty breathing. In this case, this information could be relevant to know the self-reported symptoms of a patient affected by a disease such as COVID or even a rare disease. But it could also be used to know the opinion of citizens on medical procedures something very important for public health, such as vaccinations against pathogens. For all of these reasons, we have organized the SocialDisNER task, which focuses on recognizing disease mentions in tweets written by patient accounts who write first-person experience about suffering from diseases, friends and family who share the difficulties experiences by their relatives, and medical professionals who share relevant and reliable information about diseases. To do this, we first prepared a set of language resources, including a gold standard annotated by medical experts following the SocialDisNER annotation guidelines, a large-scale corpus with silver standard quality of 85,000 tweets with mentions of diseases and other type of biomedical entities like symptoms, procedures, and pharmacologic substances, and also a set of co-occurrence matrices of mentions present in the large-scale corpus. Then, these resources were provided to the task participants, who trained their name entity recognition systems and submitted their predictions using the CodeLab platform. Finally, the participants were then evaluated using the microaverage F1 score metric. Let me go into a little more detail on the resources generated. When generating a corpus for Twitter, one of the keys is the methodology to select the content to be manually annotated. Twitter is a microblogging social network where a lot of irrelevant content is generated each day. For that reason, we have used the methodology shown in the table. In this case, instead of obtaining tweets through keywords, which generates biases and noisy content, we download tweets from a network of users who are potentially sick people, their family, or medical professionals. We manually selected 993 accounts of patient associations, health professionals, and health institutions, and from these source accounts, we download their followers, which is people with an interest in the area of health, and we built a network of more than 287,000 users. Then we download the original tweets generated by those users in the last 3 years. We discard retweets and replies to their tweets because we were looking especially for first-person experiences, and responses and retweets are less likely to be. And at the end of this step, a set of more than 12 million tweets was counted. In the third step, we filter the document collection by means of some attributes, and we enrich each tweet with additional data used to select them. First, we filter out very short tweets, non-Spanish tweets with many and tweets with many mentions to other accounts. Then we also biomedical DisNERs train with clinical text, and we keep only those tweets with at least one disease mention. Finally, we calculate first-person morphosynthetic features to maintain the tweets who had at least one first-person attribute. In the fourth step, we select tweets that contain a disease and other mentions such as procedures or symptoms, and prioritize the selection of tweets with the highest number of first-person features. At the end of this process, we had 1,500 tweets that were annotated by experts, but it's important to say that 2,000 of them were manually excluded from the final gold standard because there were very similar among them. Out of those 9,500 tweets annotated, 5,000 were used for training, 2,500 for development, and 2,500 for test. Participants trained their system and evaluated them using the development dataset, and their systems were evaluated with a test set, which was shared with 20,000 tweets as background set. As seen before, out of the 230,000 tweets, 1,500 were selected for annotation, and from the remaining tweets, the 85,000 tweets with the most diseases and first-person attributes were selected to create a large-scale corpora with silver standard quality. We applied several biomedical NERs trained with clinical cases to these tweets, and we obtained an automatic annotated corpus with several biomedical mentions, including diseases, symptoms, procedures, drugs, morphology, neoplasm, which are mentions related to cancers, professions, humans, and species, which contain mentions of viruses, bacteria, animal, and plant species. Because the NERs hadn't been trained on Twitter data, they had many false positives. So we limited the impact of these false positives in the corpus through programmatic cleaning of the most frequent false positives. If we look at the corpus statistics, we can see that diseases are the most frequent in the corpus because it was one of the selection criteria of the corpus, but we still have an important number of other types of mentions that can be used as a starting point to train systems that work with Twitter data. And also, to encourage the reuse of data for other uses than name entity recognition and to inspire possible research with the information extracted from tweets, we computed the co-occurrence matrices of mentions in the large-scale corpus. On the one hand, the disease co-occurrence matrices was calculated, and from this co-occurrence matrix, knowledge graphs could be built as the one of this image, and may be used for different things like comorbidity analysis between disease or other types of research. Another 7 matrices of co-mentions between diseases and other types of mentions have also been built for the task. With the data explained, let's move on the participation and results of the task. SocialDisNER has been very well received. We had 47 registered teams, out of which 17 submitted predictions. These participating teams come from 14 countries, including Europe, North America, Asia, and Oceania, and we had a remarkable of teams coming from non-Spanish speaking countries. In fact, 10 of the teams come from this type of countries. In addition, 15 teams have also published a system description paper for the workshop. The results of the task were quite good. The 3 best performing teams achieved F-scores of almost 0.9 and a fairly high result, and this is a fairly high result if you compare it to the disease recognition task in clinical case texts, which are more complex and with greater variability in the content of the documents. The top performing team was the CASIA team, which members from the Chinese Academia of Science and Beijing University. They scored a remarkable 0.891, and the top 3 teams were very close at the F1 score level. All 3 of the best performing teams came from academic environments, with the SCI team taking first place for industry teams. The best team in the task used an architecture as shown in the figure. It has chosen they decide to use a pre-trained general domain model, a Beto model, and they applied then a domain adaptation using data from the social media mining for health Spanish tags and our large-scale corpus. After that, they did a fine-tuning using techniques like adversarial training, child adjustments, and model fusion, taking at the end a very good result. Since several language models trained with biomedical text have been published in the last 2 years, it is interesting to see how these pre-trained models perform. 6 of the teams use biomedical pre-trained models in Spanish. In general, they obtain a positive result, especially the teams that use the Carrinos model, the biomedical model generated at the Barcelona Supercomputing Center, which was used by the 2nd and 4th ranked team in the task. The top performing team used a general purpose Spanish model doing a domain adaptation, showing that if you use a good domain adaptation strategy and very good fine-tuned procedure, you can obtain very good results also, even if the domain is not related with the domain of the pre-trained model. Most of the teams decide to use multilingual models, and in fact the 3rd classified team used this model, the SMM4H Roberta, to represent the text. And it is noteworthy that some of the teams tested the recent published general purpose language models trained on Twitter data, but they didn't obtain remarkable results. The most typical errors found in the systems are as follows. First, systems have problems identifying capitalized mentions, even though when the same lowercase version of the mention is in the training corpus. The composite mentions are often incorrectly detected because they are divided. When a mention has punctuation marks or special characters, system often split it into many individual mentions, like you can see here. And finally, mentions that are not full tokens, like this one, or that have characters such as emojis in their vicinity, like this one here, are not correctly predicted by the participating systems. In view of this, to finish, we would like to highlight the important novelties of SocialDisNER. SocialDisNER has been tasked with more participants in Social Media Mining for Health 2022. This is the first gold standard corpus of tweets annotated with disease by medical experts, and the success of the task and the fact that it is the only corpus make us think that it will be a resource with a remarkable impact in the future. A large-scale corpus with annotated mentions of various medical entities has been published, and they can be used by the community. And we also create a convention network that could be used in knowledge graph mining of Spanish short documents. Obviously, we cannot forget that we define a new state-of-the-art in extracting disease mentions in Spanish tweets with a score of 0.891. And in addition, also it's important that we have made contact with associations of patients detected, and more than 5 of them have shown interest in the results of the task and would like to get involved in the future, especially if we organize a rare disease detection task. Here you can see the summary of the highlights of the task. And before I finish, I would like to mention the people who have made this possible. On the one hand, to the rest of Social Media Mining for Health workshop organizers, especially Graciela and David from Sinai Medical Center, who are always helpful and always have helped us with the technical promise on the Codalab platform. And of course, to the rest of our team at the BSc, with a special mention to Eulalia, that is the medical annotator, and Daryl, who has taken care of most of the technical aspects of the shared task. Obviously, we cannot forget about the fantastic scientific committee who have provided us with interesting ideas, and we hope to collaborate with them in the future. If you want more detailed information, you can check the information written in the overview papers that have been published and presented in Calling 22. One of them is only about SocialDisNER, and the other is about the complete shared task overview. They are just published, so you can find on the calling proceedings. Also, you can access the data on the website, and you can download both the data used in the task and the annotation guidelines. Thanks for your attention.